Hey there. This is the review that we're going to do to prepare for our test tomorrow. This is really just the in-class review game. I'm just going through the problems that we would have done in class. You still have the review worksheet stuff that would be homework in addition to this. This is just if you wanted some extra verbal practice, I guess. All right, let's start by doing a few limit problems. This is not all-inclusive. This is just to get our mind back on how do we work through limits, remembering that we have three methods. You're always going to want to try direct substitution first. If that doesn't work, then you might look at a table or a graph, or do so. Well, to be honest, even before you go to a table and a graph, we're going to try to use some of our algebraic strategies to reduce it so that we can make the direct substitution work. If that doesn't work, that's when we go to the table or graph. All right, so looking at this one, I just kind of gave you kind of a messy, weird looking one, but we can just do direct substitution on something like this. Don't forget that that's always your first check. If you plug 0 in for x right here, this is just 0 squared, but 0 squared is just 0. And e to the 0 would just be 1. Okay, let's keep going. On this one, when we try to do direct substitution, plugging a -2 in for x is going to get us a 0 in our denominator. So we want to look at another algebraic strategy, some way to reduce this that maybe would allow us to do that direct substitution. And it is a fraction, but it's not one where you have two fractions and you're trying to get a common denominator. Really, this is more of a factoring one. If you look at your numerator, we could factor that to an x plus 2, x minus 2. And by doing that, you're now allowed to cross off these x plus 2's, and all we have left is an x minus 2. Now you're going to be able to do the direct substitution. If you put in a -2 right here, -2 minus 2, our limit is -4. Okay, do you remember the other strategies? Remember rationalizing a denominator? If you have separate fractions, getting a common denominator and merging those together. Lots of different ways of maybe trying to simplify that problem. Now this one is similar to the previous one where, oh, maybe I could factor it or something. Now, I really wish I would have put, in fact, I might even change it. Let's just change it. Instead of x approaching 2, because if you look at it, that's another one where you can just do direct substitution. And again, that's great. That's best case scenario. But let's pretend that this was an x approaches -9. Okay, now you wouldn't be able to do the direct substitution on it. But you also, if you look at the numerator, it's not really going to be factorable to where anything's going to happen. So this would be the example where now I'm going to probably go to a table and look at what's going on this one, or maybe a graph or some way. If you choose to do that, then you've got to show me work for that. If on your test, I am going to want you solving these algebraically, if at all possible. And this graphing and table are last resort. And I probably would even provide you a graph and a table if that's the method I was wanting you to use. Okay, so on this particular example, if we were to graph it, I'm going to say that this is going to have a vertical asymptote at -9. And it's going to be one of those ones where it's approaching infinity, which we say no limit. And I'm just doing this off the top of my head. Really, you would want to graph it on your calculator and look at it and give yourself a true sketch. But this would be one I'd say no limit. And remember that if you write no limit, you're going to have to tell me a reason. And this one would be considered unbounded. And again, it's probably doing something like this, and that's why I would write that. All right, here's a little harder one. And on this one, I do have the multiple fractions going on. So I'm going to want to combine these two fractions into one because I cannot do the direct substitution. So I'm going to try to do some sort of algebraic procedure to see if this will reduce. So if I'm going to do that, the common denominator here is going to be a 2 with an x plus 3. So common denominator, 2 with an x plus 3. And then I'm going to have a 2. And don't forget that that negative has to distribute. So it's going to be a minus x minus 3. And then this is all over x plus 1. But probably what I would want to do with this is instead of dividing by that x plus 1, I'm going to write it out to the side as a fraction and multiply by its reciprocal. So in my numerator, I have a negative x minus 1 over 2x plus 3, and then I'm going to multiply it by 1 over x plus 1. And at first glance, it doesn't look very nice, like nothing's going to reduce, except I actually can see that I could pull a negative 1 out of this one, and then it would match with that denominator, so I could cancel the x plus 1s. The x plus 1 was my issue with doing direct substitution. I missed my little negative right here. Okay, so now I think I'm going to be able to plug in this negative 1 and do my direct substitution. So the only thing that's left in the numerator is going to be this negative 1. But in the denominator, I'm going to have to substitute negative 1 in for x. So that would be negative 1 plus 3. So that's a 2 times a 2. So my answer on this is negative 1/4. Okay, so that's it with the limits. Now let's talk about doing the difference quotient. This was, we spent a couple days kind of working through this difference quotient. So there are definitely problems on your test that you have to show me that you can use the difference quotient to find a derivative. Now, I'm not going to give you terribly hard functions since I know we know the power rule now, but that just means that you're going to have to do a really nice job of showing me that you know how to use the difference quotient. So remember that if you're looking for the derivative, it's going to be a limit as h approaches 0 of, and now what I'm going to do is I'm going to plug x plus h in for both of these x's. So remember our trick, I'm going to sneak it up here. It's an x plus h that I'm going to have to square and take times 7 in one shot. So that's going to get me a 7x squared plus 14xh plus 7h squared plus x, but x is now x plus h. All right, that's f of x plus h minus the function itself, so that's a minus 7x squared and a minus x, and this is all over h. All right, so that's the first non-negotiable step that I need to see. I need to know that you recognize the difference quotient is a limit. You understand how to do that x plus h thing. Hold it. Your second step always has to be the simplified version. Now, the simplified version still has not evaluated the limit, so we do keep it there. And now you start to simplify things. So the 7x squareds can cancel. The x's can cancel. And remember that your goal is that everything that's left has an h because you're wanting to divide by that h. And it does. So then my reduced version is going to be a 14x because the h will reduce plus a 7h. And then don't forget this h out at the end. And h divided by h is a 1. So you got to have that plus 1. And then your last step is go ahead. Let's evaluate the limit now. We got rid of that denominator. So your final answer is the derivative. The limit is now gone because we're going to plug 0 in for h. And I'm going to have 14x plus 1. Now, ideally, you should be able to look back and use your power rule and check that and make sure that it agrees. Now, if it does not agree, well, I'm going to trust my power rule. So you would want to go back and troubleshoot. Now, abracadabra kind of, my answer just is correct. And these supporting statements or supporting work doesn't match what the answer key is, I'm counting off for that. So no abracadabra, it's got to match. Let's try a little bit harder problem. This one is a fraction, and these take a little bit more work. So we're going to start off. It's still finding the derivative using your difference quotient. So it's the limit as h approaches 0 of -3 over x plus h plus 5 minus the function. So it's going to be minus a negative. That's really going to turn into a positive then. 3 over x plus 5. And this is all over h, but I'd rather do a times 1 over h out on the side. Okay, so now you're going to get your common denominator, and these are not similar denominators at all. You got to take each one times the other. So this is an x plus 5 on this side. This is an x plus h plus 5 on this side. Okay, so common denominator, x plus h plus 5. You can FOIL these together, but you don't really need to. I wouldn't take the time because it's going to fall out when you go do your direct substitution. So don't mess with it. Okay. When I distribute up here, I'm going to have a negative 3x minus 15 plus 3x plus 3h plus 15. All right, now you're ready to do all of your reducing. So the 3x's will cancel. A negative 15 and a positive 15 cancels. Okay, that worked nice. So I have a 3h on top, but that h right there is going to cancel with that h, which is what I need. So then what I have is my simplified version here. The fraction ones usually took one more step because they just were a little bit messier on that common denominator. So my simplified version is a 3 over x plus h plus 5 and an x plus 5. And now when I do my direct substitution, that first trinomial is going to turn into a binomial. So it's going to be an x plus 5 and an x plus 5. So we could just say that the derivative, what I'm finding most people do is they just write 3 over x plus 5 and then just square it instead of writing it twice. And then that's your derivative. Now, once you've shown me that you can use the power, or that you can do the difference quotient on a few problems, we'll be done with that, and we'll use the power rule for the rest of the test. So just a real quickie power rule review here. You're going to take the power times the coefficient, and then you subtract 1 off the power. This is assumed to be a 1, so when you take it times the 2, you get a plus 2, and when you drop the exponent by 1, you just x to the 0, or it's just gone. So there's your derivative. Now, one of the things that I need you to remember is where this all started, and it really was, remember, when you find the derivative, that's actually 3 things, all in the same thing. It's the instantaneous velocity, it's the slope of the tangent line, it's the derivative. They're all the same question. Now, on this one, I've got a position function of an object thrown in the air. Got it. It says find the instantaneous velocity at 3 seconds. Okay, so the first thing I'm going to do to find the instantaneous velocity, that means find the derivative. So I'm going to have the derivative using the power rule. It's going to be negative 6t minus 9. But since this one has an exact spot that I'm checking, I'm actually going to find the derivative at 3, which means plug 3 into your derivative. So that's going to be a negative 18 minus 9, so a negative 27. Now, if you think about what's going on this problem, the object was thrown in the air. If my velocity is negative, what that means is it's on its way back down. So I don't know that I have to write that it's negative. I almost would say I would always make a statement of what that really means. So the instantaneous velocity on its way down is 27, and then think it's velocity, it's a speed, so let's be sure that we label it. This one is in meters per second. Now, I do want some sort of notation that explains this negative. If you just leave it negative, I guess that's okay, but don't just write 27 meters per second. Clarify that it's on its way down, and that's why the answer was negative on that. Okay, this one says use the derivative to find the relative min and max of this function. Okay, so this is a cubic. If you'll recall, the derivative is the slope of your tangent, and when you're at a min or a max, I'll just throw a little sketch out here to the side. When you're at the min or the max, the tangent line is horizontal, so its slope is 0. So if I can find the slope of the tangent line, which means finding the derivative, so you can't find the min and max like using your graphing calculator. That's not what we're talking about. You have to show that you know that you're going to find your derivative first, again, using the power rule the rest of the time. And now I'm going to set that equal to 0. This looks like a factoring problem. I'm going to factor out a 3x. And so I have two spots where this is going to happen. So it's going to happen when x is 0 and when x is negative 2/3. Now, given that it's just a standard cubic here, I'm guessing it maybe does what I have shown here, where a cubic has to start low and end high, and I have two spots here. And if I only had one spot, I might start thinking there's a turning point or something in there, or something weird might be happening. We can always do a sign chart to test that for sure. That's coming up on the next one. But in general, what you find here are the x values. I need to find the y values. So to find the y values, you always plug it back into the original function to find y values. So I'm going to find f of 0. Notice my notation shows I'm putting it in the regular function. And then I'm going to find f of negative 2/3. All right, the first one's easy. When I plug in 0 into the original function up here, I'm going to end up at a negative 1. So that means I've got this ordered pair 0, negative 1. All right, when I put in the negative 2/3, I've already done the work on this. So I got a negative 0.55555 repeating. Do you remember what that means? What is that as a fraction? It would be negative 5/9. Remember, repeating decimals are just over 9. Okay, so those, now, which one do you think is the min and the max? Remember, we try to decide that by looking at what a cubic does. And as you move from left to right, assuming that your leading coefficient is positive, it's going to have this shape to it. So as you move left to right, the first one is a max, the second one is a min. So thinking from left to right, you would actually come across this negative 2/3 first, and then you would hit the 0. So this negative 2/3 ordered pair, that's your maximum, and then the 0 one is your minimum. So be sure that you indicate which one's which. So this one's the min, and this one's the max. On this problem, it says use the derivative to find the vertex. The vertex. It is a parabola. It is an upside down parabola, but they want us to find the vertex. The vertex is right here. Really, that's just another way of asking for the maximum. Okay, so let's find the maximum. That's all that means. So that means you have to go do your derivative. And then remember again, your tangent line is horizontal, so you'll set it equal to 0. Okay, and then my x is going to happen when x is equal to 1. And then to find the matching y value, you plug it back into the original. So that's going to be a -2 plus 4 plus 2. So that equals 4. So your vertex is going to be 1, 4. All right, this is find the slope of the tangent line of this function. Okay, the slope, lots of just like different ways. I'm asking you the same thing, but you have to really have a full understanding of what's going on. The slope of the tangent line is just the derivative. All they're asking me to do is find the derivative. Now, because this is a parabola, the slope of the tangent line will vary depending on where you're at. So there's not a single number answer for this. Now, if they dictated, like, I want to find the slope of the tangent line at this spot, then at the end I'd plug that in. But in this case, I would just leave it as this function and not have an exact number answer. This one says write the equation of the tangent line. All right, so to write the equation of a line, I got to know a slope and I got to know a point. Now they're telling me that they want it at x equals -3, so that's going to end up being my point. And to find the slope just means finding the derivative at that particular spot. Okay, so I'm going to start off. I'm going to go ahead and I'm going to find the derivative. This is going to help me find the slope, but I want that derivative when x is -3. So that's -6 plus 2. So that's a -4. So right now what I have is the slope. That's my m. I also need a point. Well, I know that the x value is -3, but I need the y value. Where do you put it always to find the y value? Into the regular function. Okay, so if I put a -3 into the original function, that's going to be a 9 minus 6 plus 1. So that's going to get me a 4. So I have an ordered pair, -3, 4. All right, so with these two things now, I'm going to write the equation of the line. Y minus 4 equals -4, x plus 3. We typically would then move forward and put it into slope-intercept form. I know some of you can do this two-step process in one step. That's fine if you can do that. I feel like we've been doing this a few years now. If you can do those two steps in one, that's great. So add that. I'd end up with a -8. So this is the equation of that tangent line. All right, we're getting close to the end here. This is find the critical points. Now, the critical points are considered the min and max and turning point, whatever's going on there, and the point of inflection. So let's start with that. Find the derivative. Find our min and max. I'm going to set that equal to 0. Oh, okay, this is interesting. Look at this. All right. So when I set that equal to 0, the 3 is going to go away. I have an x squared plus 2 equals 0. Look at what happens on this one. Subtract the 2. Square root both sides. I'm going to end up with an imaginary number. So what do you think we're going to have to do here? Well, what that really means, and this is just a matter of being able to think, you just have to be able to think when you're doing these problems. What's going on? Well, it just means that my graph doesn't have a min or a max, or even a turning point. It doesn't really level off and get you a turning point. It doesn't do any of those things. Now, hang on to that thought for just a second. So I'm going to say there's no min or max, but could I find the point of inflection on this? Well, if I found the second derivative, the derivative of the derivative, I would get a 6x. And when I set that equal to 0, now that's going to work out okay. So I do have a point of inflection at x equals 0. To find the matching y value, I'll put 0 into the original function and I get back a 1. So I have a point of inflection at 0, 1. I have no min or max. Okay, here's what, if you did put it in your calculator, here's what you're going to see. On a graph, right up here at over 0, 1, it is just a very gradual cubic. It hardly even does what I just did there. It just is boom. It's just almost a straight line kind of thing. So it is going to flip your tangent line. Remember, the point of inflection is where it flips from being like above. So here my tangent line is like above the curve. But when I'm over on this side, it would be like under the curve. So that's what the point of inflection, it would kind of do that to it, but it never really levels off to horizontal, which is why there's not a turning point on it. So understanding, like, it just depends on the function. Different things can happen. Be ready for, I'm not saying I'm going to be tricky on the test. I'm not. It just, I want you to be able to think and understand what's going on. Okay, so this is our last question. This is kind of the all-out, full-fledged, it says it's a challenge one, and it's because there's a lot of stuff I'm going to be asking for here on this one. So it wants to know where the function is increasing, and it's just saying increasing, but on your test, it would be increasing and decreasing. Okay, it's not a very pretty function, but actually I kind of purposely made it look like this because it's actually going to come out pretty decent when we find our derivative. Okay, so increasing and decreasing. Remember, the function will be increasing if your derivative is positive, and it will be decreasing if it's negative. I'll expect to see a sign chart on this. So the first thing you're going to do is go find that derivative. Using the power rule, I gave you all these fractions, but these fractions really make it come out nice. So that's really just going to end up being an x to the fourth. And when I take a 3 times a 2/3, that's just going to be a 2. So minus 2x squared, and then a plus 1. I am going to set the derivative equal to 0 to find the min-max turning points kind of information. So this is a little trickier function, but it's still factorable. You've got x squared, 1 and 1, really pretty easy. They're both going to have the same sign, so they're both minuses. Oh, how nice is that? That's a difference of squares. So I have an x plus 1, x minus 1, but I have it there twice. Okay, well, got it. So ultimately, what I'm going to end up with is x is going to equal a plus or a minus 1. Now, those are going to be the values that I put on my sign chart. So let's set up a sign chart here. And we're going to put test numbers in. Do you remember where to put the test numbers? You should be putting those into the derivative. So show me that. Show me what you're plugging in. So in the derivative, I'm going to put in, I guess, a -2. And then I'm going to put in a 0. And then I'm going to put in a 2. And I'm looking at what ends up happening. So I'm putting those into our derivative right here. So if I put in a -2 to the fourth, all right, that's a 16. And then it's squared, that's 4 minus 8 plus 1. And remember that the big thing I'm looking for here is whether this ends up being positive or negative. So that's a 17 minus 8, that's a 9. So it is positive when it's on this side here. If I plug in a 0 into the derivative, I'm just going to have 0 minus 0 plus 1. So that's positive. And now let's plug in a 2. So that's a 16 minus an 8 plus a 1. Okay, we're back to a positive. Okay, now look at that. That's weird. It's always positive, which means that my function is always increasing. So find where it's increasing. It's increasing from negative infinity to infinity. Now, something's happening. And so then I would say it's never decreasing, but something's happening at these points. Do you know what that means when you have a like back to back plus plus? Okay. Normally our functions will increase, decrease kind of thing, right? Increase. They go back and forth. The only way that you're going to have it increase is if this comes up and is increasing and you get one of those turning points where it kind of levels out and then keeps going up. And then it has to do it again kind of thing. Now, because I have all pluses. Now, actually, yeah, it would ultimately that's what this graph would look like. It was a fifth degree function. So it starts low, ends high. And if you put that in your calculator, it'd probably look something similar to that right there. Perpetually increasing. I'd write negative infinity to infinity. Okay. So understanding there when a turning point is going to occur. If you're ever in question, like, I don't know if this is a min or a max or a turning point, your sign chart is what will for sure dictate that to you. Okay, that's a very good sampling of the types of problems you're going to have to be able to do. Be sure that you get all your review worksheets done too, though, because this is not necessarily an easy test. So good luck. Work hard.